Okay, let's, I guess, get started. First thing, of course, the project is due on Thursday. Any questions about the project or anything like that? Okay, next class I'll talk about the final and, and what we'll go from there. Okay, any questions? Okay, so what I'd like to talk about today is, it's funny, when you start to prepare, again, I've been teaching this course for about, 15 years now. And at the beginning, first of all, data science was a big, hot buzzword, okay, which is less so today. I know now today machine learning is the buzzword that's sort of eaten some of its lunch. And big data was a buzzword, okay? That it had kind of suddenly been realized that you could do analysis of all of Twitter. You could do analysis of the entire web. You could look at all the images on huge corpora, okay? And what was exciting about kind of the big data time was kind of this realization that there were all these possibilities because there was a lot of, there was data that you could work with. In general, working with data gets harder with size. And, what I'd like to talk about today is some of the issues about working with large data, larger data sets. And as I was preparing this time, I kind of realized that when people think of computational bottlenecks these days, it's always, I think, in terms of how much GPUs there are. The GPUs are what is defining the computational bottleneck on things. But in a lot of applications, it's just simply still the volume of data for still doing things that are counting, that are collecting, that are removing duplicates, that are doing a lot of other things. And this is kind of the aspect of data science that I'd like to talk about today. Some of the systems issues associated with working with data sets when they get very large. So what does very large mean? Well, there are all these, you can gather statistics and they're always out of date when, when we were, the moment they're out. But the latest statistics that I've found were something like Twitter had 500 million tweets a day at that point. Now maybe that it's X and everybody's gone to blue sky, that's gone down, but that's still a lot, okay? Facebook supposedly faces 4 petabytes of incoming data per day. That's presumably new posts, and that's new images, and that's what you clicked on, and all this kind of stuff. Google was processing, order of 10 billion queries a day, okay? So if you're going to be working at one of these companies, somebody's job has got to be about the management of this kind of data, and in order to make sense of it and make something useful out of it. When people were talking about big data, okay, they sort of broke data in, kind of defined it along 3 different kinds of axes, okay? One axis was how often were you going to be dealing with the data, okay? There's real-time applications where you've got to be dealing with you've got to be dealing with a customer in the next millisecond, down to times when you're doing jobs that are basically batch jobs that happen once a day, once an hour, something like that. The data that you got on, big, in many cases of what we think of as big data, typically web type stuff, you tend to have a lot of variety, okay? At the low end of variety are things like databases. Databases, everything is a column, everything is probably a number or a text thing. up to kind of full social media things. You've got video, you've got text, you've got a lot of other things to deal with. Okay, and that changes your thinking. And the other V was a question of volume. Okay, that data sets come from the sizes of, I will say, megabytes all the way up to, we said, Facebook gets 4 petabytes a day. That means that maybe they're up to like zettabytes of storage in-house, okay, and stuff like that, okay? So different problems have different, the aspect of what goes into them is quite different. Now, once I was talking to somebody, an algorithms person I know, okay, about big data, and he said big data is bad data. And this kind of, I thought, was an interesting idea. So what happens, where do big data sets come from? They tend to be collected by opportunity. The reason, Facebook collects 4 petabytes of data is not so much that they want to collect so much data. It's that they have so many users and the users want to do things. So when you're analyzing the data that's found from, from many applications, okay, it's usually the data got constructed as a result of opportunity instead of design, okay? If you really wanted to know something, ideally in the old days you would construct a specific technique to get exactly the data that you wanted. Typically, data analysis in these big companies is about analyzing the data that you have. And there are various things that are problems when it comes to looking at data sets that get built by all the tweets on Twitter, okay, all the posts on Facebook. One thing is that if you want to interpret it over a broad population, you're not dealing with all the people in the world when you're looking at tweets. You're looking at all the people who are on Twitter, and this is going to be a biased population. Obviously everybody's got to be somewhat literate on Twitter. Okay, obviously, so you get a bias based on, who's participating. You have to separate out the spam and machine-generated content, okay? Again, we had a company that analyzed Twitter data for a while, so that's why I guess this is the example that I kind of meant. We were trying to figure out what were the feelings about people towards products by how they were talking on Twitter at that point. And of course, we were limited to the kind of people who posted on Twitter. We had to deal with spam and machine-generated content, okay, the so-called bots, okay, and a large fraction of what you would see on a on a site these days is machine-generated, and now AI-generated is a different kind of a problem because those are, in some sense machine-generated but harder to separate from, human posts. There is a problem that with all text there is a power law, okay, associated with it. And with almost everything in the world that you have, if you look at how much people post on Twitter, there will be a large number of people who post nothing. There will be a small number of people who seemingly do nothing but post on Twitter all day. And, you end up getting strange amounts of redundancy, okay? Like, again, we were interested in using Twitter to analyze what people were saying about companies, okay? And how much do you think people say on Twitter about, let's say, Apple products? I think that's something you'll agree people say a lot of. Now, one customer we were trying to get was an airplane engine manufacturer. He wanted to know what people were talking about his airplane engines on Twitter. And how much do we think people were talking about airplane engines? Okay? If he had a crash, they would be talking about it, right? But but so this was kind of a problem that you end up getting, there's a big range of, the amount of information you have about certain things. And you also tend to get, wild temporal fluctuations. If you're analyzing Twitter, what's different now than was true 2 years ago about Twitter? Is there anything that's changed about Twitter in a big way? What? The name has changed. Why did the name change? Well, the owner changed. And what happened when the owner changed? Okay? One thing they did is they closed down all the APIs for researchers, so that's why we don't use it too much. But in terms of the content on Twitter, what has changed? Okay, is there any reason to believe it says different things than it said before? Certainly the moderation policies have changed on Twitter, right? Certainly you hear rumors of people being chased off because they don't like the politics or the sound of this thing. If I was trying to monitor what public was thinking about, okay, there would have been a change in the world that happened because of external forces to Twitter. That's hard to, let's say, detach from the signal that I'm trying to measure. And these are the kind of things that happen with found data. Any questions or comments about this? Yeah.
Nowadays, people in Facebook, people hashtag BMW, and with their content, they add about BMW to make it reach better in their post.
Okay, so you're saying that if I wanted to talk about, let's say, baseball, but you're telling me that I want someone to read my post if I have hashtag BMW.
And long details about BMW appended after my post.
Okay, so that sounds like you're talking about running a commercial in a post. Okay, again, if this is the again, so now the question is to try to interpret what that means. Okay, again, if we wanted to try to interpret what they're saying about the product, okay? Factors like that, if people are using that to game the, ranking system for posts, which is what I think is what you're saying, then that would be another external factor that's kind of hard to detangle from what we have. That doesn't mean you stop analyzing Twitter data, but you realize you've got to kind of be aware of, of these kinds of issues. Any questions? Okay, so now historically, when people were in the big data era, when people were looking at machine learning, a lot of what is the kind of classical machine learning stuff doesn't scale very well to huge data sets. We've talked in class mostly about model methods that have relatively few parameters, okay? And if you have few parameters, you can't train on, you don't benefit from having 1 billion examples if you only have 1 million free parameters. When you're dealing with large data sets, the algorithmic complexity has to be near linear if you're going to run work with that scale of data, okay? If you're going to be using matrix methods, these matrices had better be sparse, okay? Because you're just dealing in memory with an n by n matrix that for large n is going to kill you because it's quadratic. So most machine learning methods were not actually as well suited to the era of big data as we would like. We know now that, again, these foundation neural network models do seem to train successfully on huge amounts of data. That said, they're still kind of to be done by relatively few parties with tremendous amounts of resources. You can imagine that quite often it's a more common thing that you have a website with a log that's been hit by many millions of times and you want to analyze it, okay? in a world where these kind of foundation models, you're better off using somebody else's foundation model, okay, and then something specific with what you do with your own data. One of the things that you can do with big data that is different than training a big model is training a large number of small models, okay? If you think about personalization, okay, Google, if you think about it, the people Google who shows you ads, okay, or any of these websites, they're showing you ads, okay, how is that system kind of working, okay? It's got to be the case that every person on Facebook, okay, or Instagram has to have their own kind of personal model associated with them, so that you're showing them ads that are particular to what you're doing, okay? And so when you're talking about personalized models, now this is something that tends to benefit from large numbers of amount of data. Why is it? Are they training a foundation model for each individual person on Facebook? No, okay? They do have one central foundational model that they probably do to figure out what people like for ads. But if you've interacted with Facebook enough, okay, they have enough data on you to build a small model, okay? And this is kind of the way that I think big data is more generally used within companies and things. You think of it in terms of training a large number of simple models rather than, a large number of very complicated, either one very complicated model that does everybody, or or large models on individual people. Any comments, questions? One other thing that is great about having big data situations is that you can throw much of it out and you still have enough data to do what you want. So one of the important tasks in most big data problems has to do with how do you filter away things, okay? How do you remove duplicates, okay? If you're analyzing Twitter, or if you're, even these days, if you think one of the big kind of data problems that people have is setting up data to train these foundation models. If you are working at OpenAI, there is somebody's job at OpenAI to take, the web and all the books and all of this and reduce it to training data for these models. There has to be a fair amount of pre-processing that is done in order to make that kind of a data set interesting. One thing that they probably have to do is to filter away duplicates, okay? There's got to be 100 copies of Wikipedia on the web, okay? They have to filter that out. There are things in, data sources in other languages and in other, video data you may not want to analyze as text. There's a fair amount of filtering, okay, or hard to interpret data that they want to throw away. Again, when we were analyzing the Twitter feed, okay, English at that point accounted for 34% of all the tweets on Twitter. Now it accounted for 100% of our customers, okay? So, since there was a sizable cost for us to process this, okay, it was meaningful, it was worth it to throw out anything that wasn't English before doing our analysis. And so filtering is kind of an important job. And one of the, important ways, one particular aspect of filtering that's kind of interesting and important is that of sampling or subsampling data, okay? Several times in this class we have seen that, that we might have a desire to take our data and produce smaller samples of it. When we were building models, we talked about separating training data from evaluation data and kind of intermediate testing data. This means that there's got to be a problem that takes as input all your data and partitions it into these three sets, okay? There are, we have talked about, the idea that, when you have building simple models, okay, you only have a small number of parameters. You would like, it doesn't benefit from training on too much data relative to the number of parameters. If so, doing some kind of sampling enables you to, have the right size data for what model you're building. So often it pays to, we have a problem where we're going to want to take our data set and make it smaller by throwing stuff out. So there are different approaches to subsampling data. And, and it's worth thinking about. Suppose I only need n records. I'm given a huge number of records, big N, and I want to end up with a little n records for my training set or my evaluation set. How can I construct a sample of that? The simplest way is to take the first n records. What's bad if I take the first n records from a file or collection of n of big N data sets? Okay? Suppose, let's say, I was trying to come up with a text sample. Okay? If I took the first n records from Wikipedia, are there going to be biases in that? First n articles, let's say. Okay? What kind of article biases would I see? Okay, yeah.
Take alphabetically, then with A or A starting with A or similar kind of text we would give.
Right. So if I did it alphabetically, obviously I might only get through the A's, okay, if I did Wikipedia articles. And there are strange biases when you take records and you take only the ones with the beginning part of the A's. There are more Arabic names that begin with A than other letters. And there are fewer Chinese names that begin with A than other letters. So if I were sampling the class based on just the A's, I would not end up with a representative sample. If I had a log and the log was accumulated, like logs are typically by appending at the end, if I take the first n record, okay, I will end up with a temporal bias. I'm only going to get old data. If I look at people by, let's say, certain numerical codes, even numerical codes encode meaning, okay? How many of you guys have social security numbers? I think does everybody in here have a social security number? Okay. What's the first digit of your social security number? Now, how many digits, how many possible first digits are there? Not 10, right? Does everybody agree it can be a 0 through a 9? How many people's first digits 0? Nobody. How many's first digit is 1? Nobody. How many's first digit is 2? 1. How many's first digit is 3? Nobody. How many's first digit is 4? Nobody. How many's first digit is 5? Nobody. How many's first digit is 6? 1. How many's first digit is 7? How many's first digit is 8? How many's first digit is 9? How many people didn't lift up their hand? Okay? Okay. That wasn't the reaction I was looking for. Okay? But I was expecting that that most of you were going to have the same first number digit on the Social Security number. And The reason is because when they assign Social Security numbers, they do it, the first 5 digits encodes where you were when you got your Social Security number and where you, what year you got it, okay? And all of you, I think, got your IDs numbers, most of you got your ID in New York. Where'd you get your Social Security number from? New Jersey, okay? Who else had a weird, was the only one who was the only 0 we had here? No one. Who was the only, let's go back. Who was a 9? Where did you get your Social Security number? New York. You got it in New York, okay? Who was an 8? Texas, okay? Who was a 7? Where were you? Georgia, okay? So again, there are biases numerically, even in ID numbers, that end up having meaning. So Social Security numbers I picture as being a fairly random thing. The first digits are not random. The last digits are fairly random. The last 4 digits are kind of given in sequential order. So those are sort of random. Okay, any questions about that? Now, the obvious way to get N records that are seemingly selected uniformly might be to sample them with probability big N over little n. If we have big N records and we sample them, we go through the file and we sample them with probability Pn, little n over big N, we are going to end up with what? An expected little n records, each of which are uniformly, equally likely to occur, right? What's good or bad about that? Well, generally that's good. That seems like that will avoid the biases we talked about before. But there are still some problems with random sampling. One is that just some statistical irregularities will mean that some groups are going to get oversampled or undersampled just by the variance of chance. Okay? Random sampling is not uniform, is not reproducible. Okay? If I try to do this kind of random sampling, and I said I had a big file, I did a random sample, I got these results, somebody can't reproduce that without, you can't reproduce that unless you have my exact random number generator and the seed. Okay, so that's a problem. And the other thing is, suppose I wanted to try to find a sample that were for, let's say, training, testing, and evaluation. If I have a huge N, you might say, well, I want to sample, I want to end up with 1,000 training records, 100 test records. I'll set my probabilities appropriately. There is no reason why the random sampling is not going to end up putting the same training value in the evaluation set, which is exactly what you're trying to avoid. You'd like them to be independent partitions. So random sampling is not actually, does have some problems. It also doesn't give me the exact number of records I want. It might give me more records, it might give me less records. Any questions about that? Okay. Another way to develop samples that actually avoids these problems, some of these problems, is uniform sampling. Suppose I take all records that are congruent to I mod m, okay? So maybe I start out with I equals 3. I'll take the third record, the 3 plus mth record, the 3 plus 2 mth record, ... What's good about this approach? One, I know exactly how many records I'm going to have at the end. If n is, if I know what my big N is, I know exactly, I'm going to get exactly as many records as I want. This is something that is reproducible and quick. Okay, all you need to know is what I and M are. And if I want disjoint samples, how do I get disjoint samples? Okay, basically I pick a different value of I, right? If I have, instead of saying 3 mod 2006, I could have 4 mod 2006. And that sample is going to be the same size and independent of what we want to do. Okay, this was the sampling method Twitter used in order to get, they would give out, the API would give out 1% of the tweets for free to anybody who made API calls. How did they decide which tweets did they give? It would have been bad if they did random sampling for each person who was being asked, because then eventually all the tweets would get out. If you had 100 different machines calling the API, you might get almost all the tweets. Okay, this way they could modulate what percentage of the tweets you got without doing any randomness, without doing anything. Any questions about that? Okay. Now, there is a statistical method for sampling that is very, very important. When somebody I remember was reviewing my book, he said that, he didn't talk enough about stratified random sampling. Okay? What is the idea of stratified random sampling? Suppose you want to sample your text and make sure that you're not over or underrepresenting any group. Okay? Let's say that you are, doing polling. You might want to make sure that you have as many. What fraction of the people in the country are men and women? It's about 50-50, but not exactly 50-50. Maybe you would want, if you wanted to get a poll, a poll that was truly representative, you'd want to make sure you had as many men in it as you had women in it. You'd like to make sure that the percentage of whites and African Americans and Asian Americans corresponded to what was in the population. Okay? So what is the idea of stratified random sampling? The idea would be that in the technique of random sampling, as we talked about it before, says I'm going to pick people without bias, and therefore I should end up with about the right number of men, about the right number of women. Okay? Stratified random sampling says, tell me how many, what fraction of the population is men, what fraction of the population is women. Then if I know that 49% of the population is male and 51% is female, I don't know that that's true or not, but I would then explicitly pick that fraction from each subgroup. Does everybody see what's going on? You're going to define your subgroups in advance, and you're then going to sample according to the population. In this case, we live in a world where a quarter of the people are white, half the people are black, and a quarter of the people are gray. If I want a sample of 4, well, I'm going to pick 1 from the white group, 2 from the black group, okay, and 1 from the gray group. Any questions? So what are the advantages of stratified sampling? Okay, well, if you think about polling, okay, you can imagine that there are subgroups of people, okay, that have very distinct opinions. Let's imagine that there was an election where the men overwhelmingly wanted one candidate and the women overwhelmingly wanted another candidate. Okay, and you're trying to read the population. Okay? Now, who's going to win that election? That's what you conduct a poll for, right? If you don't, sample in ways that captures the right percentage of each group, adding up the total is not going to give the right answer for how people go. Okay? When you have very, very small groups, okay? Again, I happen to be Jewish, okay? This is a small percentage of the population that is Jewish. Jewish people may vote in a very specific way, okay? If your sample does not have the right number of Jews, okay, you're going to end up getting a bias in there. And if you have a group that's a very, very small, a relatively small group, it's easy to get too few of them or too many of them. And that would kind of skew the sample. So that's why the stratification is kind of important. Okay? Any questions about that? So what is the problem here? The good thing is that stratification can produce a more representative sample. The bad news problem is that you have to kind of in advance decide what you call it, what groups are worth stratifying on. Okay? You may very well decide that college students, or are college students in a group that has a unique identity and should be sampled. I've got to make a decision. Do I want to get exactly the right percentage of college students or not? You can't control everything, okay? Somehow when you're doing stratified sampling, you've got to, kind of select your groups in advance, okay? And do that analysis and have a sense of what's important for you. And if you get that wrong, then your interpretation is wrong. Okay? Now, one way to solve this problem, to do stratified sampling without supervision, without having kind of predefined groups, is to use clustering. Suppose I take the population and I cluster, I take the data points that I'm interested in, and I cluster them into K clusters. I will know for each cluster what fraction of the population is in that cluster. And the hope then is that if I pick, if I stratify on each cluster, I will get, the right amounts of different weird subpopulations, okay, without any predefined groups. Any questions about that? Okay. There's one last sampling problem I'd like to consider, which is something that people tell me is often an interview question. Okay. Suppose, let's say, we have a data set that's coming in, maybe today the Facebook posts of something, and at some point I'm going to need a sample of 100 posts randomly picked from all the posts today. If I want to end up with 100 elements, okay, I've given you a couple of ways of doing it. If I know in advance what the number of samples there are, what the total number of items there are, okay? But what if I don't know the number n in advance? I'm going to be given, I want to get a sample of size k, okay? Actually, let me just double check this. It is ultimately going to be n items that are going to be in, that I'm going to see, okay? But I don't know what n is in advance. Let me say that again because I think I got the letter wrong. K is the size of the sample I want. So in this example, I want to end up with 100 posts uniformly chosen from the samples today till the boss demands them. I don't know how many items I'm going to see in total, okay? And I don't know in advance when this is. Let me just double check the question I'm thinking is wrong. Okay. Let me try one more time. Okay? I'm going to see n items. Okay? I know I'm going to see n items. I want to end up with a random sample of k. But I don't have enough memory to store all the n items. Okay? I only have the memory to store k items. Now let's think about this problem. Now I think this is clear. In the end, I know there's going to be n items, okay? And I only have size k, so there's a stream of n items. There's only a size k, okay? How can I, how can I build a random sample like that? Okay? Any questions about what the problem is? I know I botched that one up, okay? And in fact, as I'm thinking here, I may not need to know what n is advanced, but let's say I know what n is advanced now, okay? Any question? Actually, I don't think I need that. I don't need that, okay? But what is the harder problem? I want to build a random sample of things where I have a big stream. I want to end up with k items. I don't have room to store all n of them. That's the hard part. And I want to end up with these k items being equally, equally likely to have been any of the items that I see. Okay? How do I do that? Okay? Sorry, I know I botched that up. Okay? So, what is the problem? Again, you can't store all the items. You don't know whether... How could you do that? Let's just think of different ways to do that. Okay? Suppose, let's say, I did know n in advance. What would be a way to do it? If I only have k memory and n items, what would be a way to do this in advance? Okay? One idea might be I sample each item and keep it with probability k over n. Okay? If n is big, I'm going to throw out most of the, I'll throw out most of the items. Each item that I get had ultimately a k over n chance of getting in there. But I don't end up knowing I don't end up getting a sample of exactly n, right? Of exactly size k. And I did need to know what n was, okay? So what is the solution? What if I keep an array of k elements? So at start, I put the first k elements that I see, store them in my array of size k. And I'm going to keep an active sample, okay, as I go through this, as I take the stream. Okay? Then, with each new element, the k plus first element, I am going to decide whether I want to add it to my random sample. Okay? And if I decide I want to add it to my random sample, I'm going to have to kick one of the other elements out. Okay? So that's what kind of the streaming algorithm is. Okay? Keep my working sample of size k. Every new element that comes along, okay, I'm going to have to flip a coin to decide whether I want to add the nth element to the sample. Okay? What should be the probability I add the nth element to the sample? Well, the nth element that I see should have an ultimately k over n chance of being in the random sample. So I'm going to pick I'm going to pick this, I'm going to decide to add it with a probability of k over n. I've then got to pick which one of the elements that I kick out of my array. Okay? And what I'm going to end up doing is selecting the position of the new element, the one that's going to get replaced, uniformly at random. So what is the process? For each element, okay, the new element I see, If it's the nth element overall, with probability k over n, I am going to decide I want it in my array. Then I'm going to pick one of the k positions uniformly with probability 1 over k, and then replace what was there with the new element. That's what my sampling process is. Any questions? How many people understood that? Okay, I know I mumbled that badly. Any questions about that? Okay, in the picture is stolen from someplace without a great deal of thought, so the answer is probably. Okay? So and in this case, again, I mumbled here, needing to know n in advance. I got confused. I don't need to know what n in advance here. N here is the number of the current record that I'm working with. The important thing is here, I don't know when they're going to stop. Okay, they're going to stop and tell me, now give me the sample. So I'm going to keep a current random sample of size k over all the ones that are there. Okay? Why does this work? Well, let's think, what's the probability that the first element we saw, 1, is in the random sample after n minus 1 picks? If we were, by an inductive assumption, if we are saying we're maintaining a random sample all the way along, the probability 1 is in there after k minus 1, n minus 1 picks should be k over n minus 1. This is the inductive assumption. Now, we're going to do the nth element. What's the probability that 1 survives this next pick? Okay? Well, 1, there is a probability of k over n that element n is going to get stuck into the random sample, which means there's a probability of n minus k over n there isn't. So there's the probability. What's the probability 1 survives? Well, it survives if 1 is never sampled, or it survives if n is sampled, okay, and somebody else gets kicked out. K over n is the probability that the nth element is going to get sampled. The probability I survive the culling here is there was a 1 in k chance I got picked, which means there was a k minus 1 over k chance I got picked, I got culled. I mean, I got saved. So the probability that I survived, even if n was sampled, was k minus 1 over n. What's the probability that 1 is in the sample after n picks? Well, it's the probability it was there after n minus 1 times the probability it survived. What's the probability it survived? It was this plus this. Okay, and then we end up getting the right probability at the end of k over n. Any questions about that? Okay, so that's why this stream sampling algorithm works. Okay, good. Okay, I'd like to change, so one of the things we agree is that with big data we agreed was you could sample it and throw a lot of it out, and that was good. But sometimes you're going to want to deal with still large volumes of data. And in order to do it, you want to be able to use many machines in order to do this kind of processing. And, historically, when people talk about using multiple machines to process data, there is a distinction between distributed and parallel processing. Parallel processing is what kind of, I think, happens on one machine. You are living in a world of threads. You are living in a world of multiple cores. You are living in a world of operating system processes. In distributed processing, okay, you're living in a world that happens on many machines with network communication, okay? And, you know, these days, you know, when we talk about, you know, high performance machine learning, people are typically talking about GPUs. GPUs, to a first approximation, are parallel processing, because there's a lot that's going on one machine. You have a large number of, you know, of multiplication units, in some sense, going on in parallel on one chip. But when you think about the problem that a company like OpenAI faces, if you're training a GPU, a model across large numbers of GPUs, these GPUs are sitting on a bunch of machines, the problem of training a huge model is a kind of an interesting mix of parallel processing kind of going on each GPU, and distributed processing going across, where you have to communicate at a slower rate across many different machines. Any questions? So typically, you know, again, data parallel problems are easy to parallelize, okay, or to distribute. If you can take your problem and break it into different partitions that don't have to communicate, like training large numbers of separate models, this is great, okay? What typically is harder is, you know, is when you're taking, using multiple machines and hoping to combine the results of the runs together later. That is what makes, you know, parallel processing harder. Now, one thing that I find, you know, revealing is kind of that when you're dealing with distributed processing, or you know, or parallel processing to a certain extent, where it's all on, you know, things happening on a machine, but certainly in distributed process things, the complexity of dealing with your problem, okay, grows rapidly with the number of machines that you're going to parallelize, okay? So if you have one machine, keeping the cores on your machine is relatively easy. If you have two machines, you can manually do things with multiple machines. But when you have many machines, there is a, you know, sort of a big system problem of how do you keep all the machines busy and up and under control, okay? And this is kind of, you know, you need to have programming systems that are capable of dealing with multiple machines, because weird things happen when you have large numbers of machines. Now, I think of the problem of managing multiple machines like managing a social engagement, okay? When you have one person you're trying to, you know, you're trying to figure out what to do, there's no coordination problem at all. When you have two people or a small number of people in your group, there's still some level of coordination. You guys can work it out among yourselves. By the time you have a social situation where you have a social case where you're trying to get 10 people out for a birthday party, it only works if one of them is a leader, okay? And you need to kind of have a fixed leader to rally everyone around. When you have a social engagement of 100 people, like a wedding, can you go, 100 people go into a restaurant and order different things? And there's too much chaos. You have to fix the menu, okay? When you have 1,000 people at a wedding, okay? Actually, I've once been to India, went to 2 weddings, okay? I know you guys have big weddings there, is my understanding. How many people do you know at these weddings? Okay, nobody. The bride and groom certainly don't know everybody who's there. No one knows everybody who's there. Okay? Let's say you wanted to put a conference on for 10,000 people. Can Stony Brook host the NeurIPS conference? Okay? We couldn't possibly have enough hotel room for hosting a conference that big. The coordination problems are too large, okay? There's only a small number of cities that can host big conferences like that, okay? And when you have a social organization of 100,000 people, things happen, people will die, okay? What's an example of something that happens at 100,000 people? Like attending a soccer game or a big football game, okay? You might have 100,000 people. How do we know that someone will die who attends a football game of 100,000 people that day? How many days does somebody who lives to be 100 live? You guys are hoping to live to be 100, right? I'm hoping to live to be 100. How many days does it take in your life if you were 100 years old? That's 36,000 days, right? This means that's sort of 300,000, that's 300-year lifespans, okay? So somebody is going to die on that day. There's going to be an accident driving to the stadium. Someone's going to have a heart attack. Somebody's wife is going to kill them, something like this, okay? And in fact, when you try to organize big conferences, like we once organized a conference for ACM, they have specific policies for what should you do when somebody dies at the conference that you're hosting, because something like this will happen if you have a big enough thing. So what's the point of this? The point of this is that whenever you have a big enough computing problem, you've got to worry about things dying, okay? And you guys are familiar with GPT-4. You guys are familiar with the idea that, oh my God, they bought 25,000 GPUs in order to train this thing. They had the model trained for 100 days. All the other statistics, you had enough power to light up the thing. You had a lot of but what's important? If you have 25,000 GPUs for 100 days, what is going to happen to some of those GPUs? Okay, they're not going to go to a restaurant, but they are going to die, right? And so there's got to be there's a kind of unheralded part of training these models, which was how do you do fault tolerance here? Okay. Almost certainly, a sizable fraction, a non-trivial fraction of I couldn't find what the fraction was, but a non-trivial fraction of these GPUs had to die during the course of training. In fact, if they didn't, they probably weren't running them at a fast enough clock rate, okay? And somehow OpenAI had to build a system that was going to be fault tolerant. How did they do that? Well, among things that they would keep checkpoints of the models at every given point so that if something bad happened, they could roll back. Okay, they undoubtedly had to do tests regularly of whether a GPU is still alive. Okay, and whether it is yielding fresh things and knowing when to ignore it. Okay, knowing when to detect when it was bad, things like that. Okay, and so this kind of system robustness thing is kind of an unheralded part of what's involved in training one of these big models. Any questions or comments about that? Okay, now in general, for most of these big data, for a large class of big data problems, they fall into the category of things that are handled by a MapReduce system. Out of curiosity, how many people here have ever programmed anything using Hadoop? Is there anybody who knows about Hadoop? Is there anybody here who used Spark for anything? No. So somehow there is recognized that in the kind of big data pipeline, there is this issue of how do you manage using a large number of computers for for dealing with a single large data set, okay, in a way that it is reliable It can overcome errors. It's got fault tolerance, okay? You could scale it to hundreds or thousands of machines if you wanted to, if you had the money for it. And yet you would want to program it in a relatively straightforward way. So the MapReduce computations supported by, Hadoop or other systems, okay, are a way to kind of do it. They achieve fault tolerance by redundancy. For every data item, they don't store it on one computer. You will store it on many machines, okay? And they will, on multiple machines, not many, okay? And again, there's this MapReduce architecture for programming it, which is kind of interesting, okay? So what is it? Hadoop is the system that I'm used to, okay? Because this is what we used when we were building our big tweet processing thing. We would regularly use 35 machines at a time to try to figure out what to read, to process the day's tweets, okay? Now, with all, again, if you're not familiar with them, then the differences between these things. Hadoop is kind of the original open source kind of MapReduce implementation, and it works largely on disk-based systems. So I was assuming I'm dealing with large amounts of data. Large amounts of data should be sitting on disk, okay? And so for batch processing kind of jobs, Hadoop was a great thing. Today, probably more popular is a system called Spark, which is RAM-based. It says memories have now gotten big enough. I'm going to store all the data I'm working on across in the memory on my machines, okay? So I'm going to need larger memories, but I'm going to get faster processing. And so if you want to do online kind of processing across many machines, Spark is a better thing. But both of them are based on this kind of MapReduce architecture. And it's based on the fact that many big data problems have the same basic structure. You're given a bunch of records, okay? You want to extract something from each record. You want to then take the records and sort them, okay, rearrange them, so all the records with the same something of interest are together, okay? And then you want to aggregate the results, okay, from each group, okay, and generate an output. So what are examples of these kind of big data problems? One problem would be, suppose I want to know how often every word on the web appears on the web. The web is a lot of text, okay? I'd have to have it on a large number of machines, okay? What was the way that I would like to do it? I would like to be able to count for every vocabulary word, how many times does it appear? If I have my text directed on each, partitioned among a bunch of different machines, I'd like to, for every machine, count what's the frequency of all the words that appeared in it. I'd then like to rearrange my counts, okay, of all the words, which are now spread on a lot of different machines. Get it so the counts of each word, okay, let's say I want to find out how many times the fenestrate occurred. Each machine might have a count of how many times the fenestrate occurred in what it is. In order for me to get that complete count, I've got to kind of aggregate that. I've got to make sure that all the defenestrate counts go to the same machine so they can be added up. That's the aggregation. And then finally, the final counts have to be collected across. That's like word counting. If I wanted to do k-means clustering, suppose I have a large number of records spread over all different machines. How could I do k-means clustering? What is the k-means clustering doing? I need to know for every, I start out with a current set of cluster centers. I'd like to know for each record on each machine, which of the current cluster centers is it closest to? Okay? That's what the extracting information of each interest is. So let's say I have 100 different cluster centers. I can keep the 100 cluster centers on each computer. I can go through all the examples on the machine and say, what is your, which center are you closest to? Okay? I then need to rearrange now that I know for each machine which centers each one is over to, which examples are closest to. I need to kind of compute the centroid of these things and kind of aggregate this across the machines, come up with the new centroids, and then redo this again. So a lot of the big data projects fall into this kind of an environment, okay? And this kind of an environment can be solved using the MapReduce paradigm, provided we have some support for answering the kind of system stuff, okay? How do we compensate for machines that die? How do we know when to aggregate things? Because we need to know that all of the individual workers have to be finished, okay? How do we assign what work goes to what machine? This is kind of done by the runtime system of MapReduce or Spark. This is kind of where that level of brains is in. But to program it, okay, MapReduce computations have two different, basically only two important primitives. There is for each record, okay, a map function that, given a key and a value pair, maps that pair to a particular key with perhaps some change in value. Okay, maybe you've done some computation on the data fields, okay, and you're only going to turn the presence of a word in a text to a count, okay, and you need to have a key that represents the data item that you had. Reduce, okay, is going to be something that, given a computed key, okay, takes the array of values, okay, and produces a single value out of that array. So for word counting, maybe I've got an array of values. How often did that word occur in each document? Okay? The reduced operation would, in that case, for word counting, simply average it together. If we were trying to compute the centroid of points, if these were all the points that were closest to point K, okay, then what was going to happen? We would be computing the centroid of all of these, which I guess would be the pairwise, the dimension-wise average, okay? In order to do this, somehow the mapper has got to take all the data, the records with a particular key and map it to a reduce machine that will get all the records of that key. Okay? So here, suppose, let's say we were doing word counting. Here's a situation when we have 4 machines that are map machines. Okay? Each one of them gets a chunk of text. Okay? And we learn that A occurred once, B occurred twice, C occurred 3 times, C occurred 6 times here. Okay? What are we going to be doing? The reduce the Hadoop file system, the mapping thing, is going to take every key and hash that to a particular reduce machine. So all the A's on all the different machines will go to the same reducer. All the B's on all the machines will go to the same reducer. All the C's will go to the same reducer. So what the MapReduce system is doing is you take your task, okay, you express it as, for each record, okay, collect the records with the appropriate values. The runtime system will shuffle and aggregate these things and send them to the reducers to be working on. Any questions about that? Okay, let me just double check and see where I am. Okay. So what did this look like when you programmed it? Okay. For a word count program, okay, the map function would look something like this. For each word in the text, emit a message keyed to the word that just had the word 1. That was the count for every word that I saw, right? So I'm spanning through the words. I'm going to emit a record of 1. Reduce is going to say, for any term, okay, do an iterator of all the values and basically just sum up all the records here, okay? And at the end, basically emit for that term what the sum is. This is what the word count program would look like in a distributed way. You would have the same mapping program running over all the different mapping machines, okay, on different texts. You would have the runtime system collecting these emit messages and hashing them to you're hashing the key so that it goes to the right machine, okay? Then, once we're on that, on the reduce machine, this is the reduce job that would run, that over each term that is expressed there, basically iterate over the appropriate values, okay? And the runtime system would enable this to aggregate the results over all the machines. Any questions about that? Okay, so again, this is kind of the basic picture of kind of what's happening. Messages get sent from the map machine to the reduce machine, okay? The important thing is that the same words are always sent to the same reducer, okay? And then these things can run. Any questions? There are other primitives that you would use in these kind of MapReduce systems to enable it to be more efficient. If we think about the word counting program, okay, we might want to say it's bad if we send a message across the network for every single word that appears in a single text. What might be better is that there be some intermediate reducer, okay, that kind of before emitting the count for a word across the machine, aggregated the counts, okay, from, let's say, all the words in the files. So there's another primitive for combine that's like a local mini reducer, okay, that would would reduce the amount of traffic on there, okay? And when you set up your MapReduce system, there's also got to be a partition. You've got to tell me how many machines do I want dedicated to a particular key, okay? You might want, when we were you do word counting, what is the word that's going to have the most counts to it? In English, the word the is going to occur something like, I don't remember what, if it's 10 or 20% of all the words in English are the. If you did word counting and you had 1 million machines, if all the thes are getting mapped to the same machine, aggregating, that one machine is still going to take 10% of the time it would take for the entire computation, okay? So there is sometimes a situation where you would like to partition for certain keys that are going to be high frequency, put them on a number of different machines. Okay, there's a certain art to dealing with because there is a power law here, and the highest frequency thing is going to occur so much more than other things. You want to make sure that that one bucket doesn't dominate the entire computation. Any questions? Okay, good. And that just sort of shows this thing. So what does the runtime system for a MapReduce thing? Well, it handles the scheduling of workers to tasks. It handles the data distribution. Okay, basically it makes sure that on each data file that the program you wrote, the MapReduce programs that we saw, get distributed to all the mappers and all the reducers. There's a certain amount of synchronization and error tolerance. When workers fail, tell it to restart. Okay, minimize these things. This is what would be done by the MapReduce system underneath. When we were in Hadoop, which was again a disk-based system for doing this, you were storing all the data on the local disks of the machine. Now, disk accesses are slow, okay? But if you're passing through a file as a stream, you can get much faster access than if you were randomly doing it. So for stream processing, disks are fine. You do have a world where disks go down. So on the distributed HDF file system, every item was replicated 3 times. So if a machine went down, it was possible to reconstruct the data that was on it, okay? And this enabled you to use kind of standard hardware for which had things potentially go down. That would work on it. Any questions about it? Any questions about this kind of stream processing, MapReduce, why it's a good thing or not? Okay. If not, thanks for your attention, and if you want to talk with me about your project, I'm available here after class. Okay, thank you.